Now we are going to discuss rotational vibrational spectra. That means rotational transition and vibrational transition occur simultaneously. Let's see how does it works. That means we see there are transition in between rotational levels, that is if there is j equal to 0, j equal to 1, j equal to 2, there may be transition from 0 to 1, 1 to 2, or back from 1 to 0, 2 to 1, like that. And we also saw the vibrational transition between vibrational level v equal to 0 to v equal to 1 and back. And now we are saying about rotational plus vibrational transition means some molecules can show both the transition simultaneously, mainly in their gaseous phase. So how it does work, let's see. Mainly molecules can be exist in three energy levels. They are electronic. First one is electronic energy level, then vibrational energy levels, then rotational energy levels. So these electronic energy levels are more spaced than vibrational, and vibrational levels are more spaced than rotational. So we can say that if we are considering two electronic state, the ground state can be represented as E0 and the first excited electronic states can be represented as E1. These are the examples of two electronic states, two electronic energy levels. This is the ground electronic energy level. This is the first excited electronic energy level. And the vibrational levels are distributed in each electronic level. That means if we take this one electronic energy level, there are many vibrational energy levels can be seen. That is V equal to 0, V equal to 1, V equal to 2, V equal to 3, etc. Like that, if we take this electronic level, we can also see many vibrational levels distributed within this electronic energy level. Again, V equal to 0, V equal to 1, V equal to 2, V equal to 3, etc. So vibrational transition can be occur within this within the same electronic state or from one electronic state to other electronic state. And coming to this rotational energy levels are again more closed, means their energy spacing are more less. That means each vibrational levels can be again divided into many rotational energy levels. So here we can see many rotational energy levels, say j equal to 0, j equal to 1, j equal to 2, etc. And this another vibrational level is again divided into many rotational levels, say again j equal to 0, j equal to 1, j equal to 2, etc. So to distinguish these two sets, this is a lower set and this is a higher set of rotational levels. So to distinguish this lower and higher levels, lower levels of rotational levels can be represented as J double dash and higher levels can be represented as J dash. Then if we are taking two vibrational levels V equal to 0 and V equal to 1, the rotational levels present in this V equal to 0 level can be taken as J double dash is equal to 0, J double dash is equal to 1, J double dash is equal to 2, etc. And for this higher level, higher set, it will be J dash is equal to 0, J dash is equal to 1, J dash equal to 2, like that these levels will go. Now, if we are saying rotational and vibrational transition occurring together, that means this may happen, that is vibrational transition means V equal to 0 to V equal to 1. A transition from this V equal to 0 level to V equal to 1 may happen. Rotational transition means either within the same vibrational level or from this vibrational level to another vibrational level can be occur. So we say that there is a rotational transition from J double dash to J dash. We don't know the values of J double dash and J dash. Either it can be plus or minus 1 or something other. We are not talking about that right now. We will say it later. So we have to study the rotational vibrational transition of different gaseous molecules. So if we are considering gaseous molecules, there might be gaseous molecules, there are possibilities of diatomic molecules and polyatomic molecules. For these diatomic molecules, only one possible shape is linear, just like HCl. For molecules like hydrogen and nitrogen, being homonuclear, they will not give vibrational transition. They will not give rotational transition because they don't have any permanent dipole moment. That's why they are not also giving. They also not giving rotational vibrational transition also. So we are considering heteronuclear diatomic molecule here. For polyatomic molecule, the possible shapes may be, there are linear polyatomic molecules are there and non-linear polyatomic molecules are there. For example, linear carbon dioxide, it's a polyatomic molecule because greater than 2 atoms. There are total 3 atoms. For example, non-linear, the example we can take H2O. That is, it's non-linear in shape. So we have to study about rotational vibrational behavior of these 3 types of molecules. So if we are considering the rotational vibrational transition of a linear diatomic molecule, let's see what will be the energy levels and spectra. For that, we are finding the energy required for the transition, and the transition is set like this. It is from the vibrational transition is occurring from V equal to 0 to V equal to 1 level, and rotational transition occurring from a J double dash to some J dash value, not mentioning which are the values. So to find the energy required for such a transition, that means the levels are V equal to 0 and V equal to 1. So one vibrational transition is there, and if we are considering the rotational levels present within this vibrational level, some rotational transition also occurring here. Now the energy required for both the transition, that is rotational transition and vibrational transition, occur simultaneously. So the total energy required will be the energy required for vibrational transition plus the energy required for rotational transition, and we have said that the vibrational transition is from 0 to 1 only for easier explanation. So we are considering the energy for a vibrational transition from V equal to 0 to V equal to 1. We know that it's the fundamental vibration. The energy required for one fundamental transition we have already derived. It is mu bar into 1 minus 2xc, where x is the unharmonicity constant. Its value can be 0.01 as we have discussed in the previous video. Now we have to find the delta E for the rotational transition, that is energy required for a rotational transition occurring from J double dash to J dash. So that means it will be the energy of final level minus energy of initial level. We know for a level J, the energy will be equal to Bj into J plus 1. So in the place of J, we have to put J dash and J double dash. So Ej dash will be Bj dash into J dash plus 1 minus Ej double dash will be Bj double dash into J double dash plus 1. Now B is common, we can take outside. When we take B outside and giving the J double dash to inner factors, we will get B into J dash square plus J dash minus this J double dash is taking inside, we will get J double dash square plus J double dash. Now we are opening this bracket, we will get J dash square plus J dash minus J double dash square minus J double dash. Now we will get, there are J dash square minus J double dash square. So it is in the form of A square minus B square. We know A square minus B square will be equal to A plus B into A minus B. So like that, this J dash square and J minus J double dash square can be replaced by a plus b into a minus b format, that is j dash plus j double dash into j dash minus j double dash. The rest of the terms are plus j dash is there and minus j double dash is here. Now we can see that this term j dash minus j double dash is common in both the terms in the either side of plus. So we are taking this j dash minus j double dash term outside. We will get j dash plus j double dash plus 1. This is the energy required for the rotational transition only, and this is the energy required for the vibrational transition. So to get the total energy, as we have mentioned here, we have to add this vibrational part plus rotational part. So the total energy required for a rotational vibrational transition will be equal to mu bar into 1 minus 2xc plus b into j dash minus j double dash into j dash plus j double dash plus 1. And this mu bar into 1 minus 2x is the energy required for the fundamental vibration, that is from 0 to 1. It can be expressed as a simple term mu bar 0. Now this whole term is replaced by simply mu bar 0 plus b into j dash minus j double dash into j dash plus j double dash plus 1. This is the energy required for a rotational vibrational transition, where the vibrational transition is from 0 to 1, rotational transition is from some j double dash to some j dash. So this we have to by heart. So as we have already mentioned earlier, we are now considering linear diatomic molecules, how they produce a rotational vibrational spectrum. So now we are going to check their spectrum. For that we have to consider some j dash and j double dash value. So now we are saying that what if the delta j is plus or minus 1. That means from if we are considering j double dash j dash and the lower j double dash like this. If delta j plus 1 means the possibilities are plus 1 means 0 to 1, that is j dash will be equal to 0 and j dash will be equal to 1. Then only delta j will be plus 1. And if we consider delta j equal to plus 1, again we can say 1 to 2, 2 to 3. This whole transition is with delta j is equal to plus 1. So if we are considering 1 to 2 transition, that means j double dash is equal to 1 and j dash is equal to 2. If we are considering 2 to 3 transition, j double dash is equal to 2 and j dash is equal to 3. So we have to put these values to find the spectrum of delta j is equal to plus 1 case. And what if the delta j is equal to minus 1? If delta j is equal to minus 1, the possible transition is from 1 to 0, 2 to 1, 3 to 2, like that. Now the values of j dash will be, if we are considering the values of j dash and j double dash, here j double dash means 1 and here 0, then 2, 1, 3, 2. So this set indicate delta j minus 1 case and this set indicate delta j plus 1 case. So first we are considering what if delta j is equal to plus 1. So case 1 is what if delta j is equal to plus 1. For plus 1 it will be 0 to 1, 1 to 2, 2 to 3. This will be the transition. Now we have to find delta E. Mu bar 0 is written same. Mu bar 0 plus b into j dash minus j double dash. That means 1 minus 0, that is 1 itself. B into 1 into j dash plus j double dash plus 1, that is 1 plus 0 plus another 1. So it will be equal to 2. That means mu bar 0 plus 2b we will get. Like that, if we put j double dash is equal to 1 and j dash equal to 2 in this equation, we will get mu bar 0 plus b into j dash minus j dash, 2 minus 1, 1 itself. into J dash plus J double dash plus 1, 2 plus 1 plus 1, that is 4. That means mu bar 0 plus 4b. Like this, if you do, you will get mu bar 0 plus 6b. So that means the spectrum will obtained at these values. The energy required is expressed here. So the energy required for a 0 to 1 rotational transition, if delta J is equal to 0 to 1, B is already taken for granted, it is 0 to 1 only. That's why we are considering this fundamental vibrational energy. Okay, the only changing part is delta J. If it is from 0 to 1, we will get mu bar, we need an energy of mu bar 0 plus 2b. If the transition is from 1 to 2 for rotational levels, and for vibrational level, it's taken for granted 0 to 1, we will get mu bar 0 plus 4b, like that. So if we are producing the spectrum, it will look like the mu bar 0 is, if mu bar 0 energy is taken in this point, x-axis will show energy in some centimeter inverse. So if mu bar 0 is the point for the first transition, that is from 0 to 1, vibration also occurring there. We are currently writing the rotational changes. If delta J equal to 0 to 1, we will get a peak at mu bar 0 plus 2b value, because the energy needed for that transition is mu bar 0 plus 2b. So if this is mu bar 0, this is 2b. So 2b is added to mu bar 0. That is for the 0 to 1 case. So for 1 to 2 case, mu bar 0 plus 4b. So another 2b should be added. So we will get a peak here. So this is for 1 to 2 transition. And for 2 to 3 transition, it is mu bar 0 plus 6b. So another 2b should be added. So these are the point if delta J is equal to plus 1 case. Okay. Now we are considering what if delta J is equal to minus 1. That means delta J minus 1, J double dash, J dash, and delta E we are considering. So for minus 1, we know the higher state is having low value, that is 0, 1 to 0, 2 to 1, 3 to 2, like that. Then delta E is equal to, as we have said, mu bar 0 plus b into J dash minus J double dash into J dash plus J double dash plus 1. We will get mu bar 0 plus b into 0 minus 1, that is minus 1, into 1 plus 0 plus 1, 1, that is mu bar 0 minus, sorry, here it is 2, we will get mu bar 0 minus 2b. And here mu bar 0 plus b into J dash minus J double dash, 1 minus 2, it is minus 1, into J dash plus J double dash plus 1, 2 plus 1, 3, again plus 1, 4. We will get mu bar 0 minus 4b. Like if you do transition from 3 to 2 and putting 3 and 2 instead of J double dash and J dash, we will get mu bar 0 minus 6b. So the spectrum will look like, if mu bar 0 is the point here, energy required, then the spectrum for 1 to 0 transition will obtain mu bar 0 minus 2b. So we have to subtract a minus 2b and we will get peak here. So this is the peak for 1 to 0 rotational transition, and vibration is also present there. That's why the mu bar 0. Along with that vibration, this much energy is needed, mu bar 0 minus 2b. And if the rotational energy transition is from 2 to 1, we will get a value at mu bar 0 minus 4b. So this is mu bar 0 minus 4b, means left side again minus 2b is done. Like that we will get 3 to 2 here. So all over we will get a peak like this. So this is the case for delta J equal to minus 1. as we have written here, this is the case for delta J is equal to -1. So if mu bar 0 is here, this mu bar 0 plus 2b mu bar 0 plus 4b mu bar 0 plus 6b, these are the delta J plus 1 set. And this mu bar 0 minus 2b mu bar 0 minus 4b and mu bar 0 minus 6b, this is the delta J minus 1 set. So here vibrational transition is there from V equal to 0 to V equal to 1 along with rotational transition. For this peak, the transition is from 0 to 1, 1 to 2, 2 to 3. These are delta J, the difference in the rotational energy levels. So here it is, if it is 0 to 1, this is 1 to 0, 2 to 1 and 3 to 2. So this whole set is for delta J plus 1 and this whole set is for delta J minus 1. So to distinguish these sets with the different delta J values, we can express this in the terms of some English letters. That means if for different delta J value, let's say that let's represent the sets like some name of branches. That means if delta J is equal to 0, that set should be known as Q branch. If the transition is with delta J is equal to plus 1, that set is known as R branch. So now you can guess if delta J is equal to minus 1, that set will be, we can guess P branch because it's in the order PQR. So if it is plus, if there is any plus to what will be? It will be S branch, just like alphabetic order. So this whole set can be termed as delta J plus 1, that is R branch. And this whole set can be termed as delta J minus 1, that is P branch. So this first peak where it starts from 0 to 1, it can be represented as R0 and this is R1 line and this is R2 line. Like that, if we are considering the left side, it starts from 1, not from 0, it starts from 1. So the first branch is P1 only, not P0. Here it is R0, but here it is P1. And like that, P2, P3. The rotational vibrational spectra of linear diatomic molecule can be represented as mu bar 0 plus 2b plus 4b plus 6b, mu bar 0 minus 2b minus 4b minus 6b. This is R0, R1, R2. This is P1, P2, P3. Now to find the value of mu bar 0, what we should do? It's the midpoint of P1 and R0, that is P1 plus R0 by 2, that should we do. And to find the value of B, we know that this distance is 2B and this distance is another 2B. So P1 to R0, the whole distance will be 4B. That means R0 minus P1 will be equal to 4B. So these two ideas can be used to find some answers for some questions. If they ask for mu bar 0 or B, to find these factors we can use this concept. So what we are studying, that the rotational vibrational spectra of linear diatomic molecule is a PR branch. That means there will be peak in P set, P branch and R branch, and there is no peak in mu bar 0 because delta J equal to 0 is not possible in the case of the linear diatomic molecule. So the selection rule for a linear diatomic molecule is there is P, R branches are possible. So P indicate delta J is equal to minus 1 and R indicate delta J is equal to plus 1. That means the selection rule for rotational vibrational transition of linear diatomic molecule is delta J plus or minus 1. Where we get this? It's from PR branch. The only possible branches are PR. So either you should study PR branches or you should study plus or minus 1. From one, another can be made. So as we said in the starting, we have to study linear diatomic molecule case and in the section of polyatomic there is linear and non-linear. So now we have studied that for linear diatomic molecule the spectrum will give a PR branches. And what if the case of linear, non-linear, polyatomic molecules? So we have to study it like this. For linear diatomic, if it is PR branches, for polyatomic linear, it will be PQR branches. For non-linear, we have to consider two cases, the parallel and perpendicular vibration. So different type of vibration can be seen within one molecule. We will discuss it now. So if the vibration is parallel, it will give PR branch. If the vibration is perpendicular, it will give PQR branches. So that means for linear diatomic molecule only PR branches can be seen. That means delta J is equal to plus or minus 1. For polyatomic linear PQR branches can be seen means delta J is equal to P means minus 1, R means plus 1, Q means 0. That means delta J plus or minus 1 and 0 both are allowed transition for a case of polyatomic linear molecule. For a polyatomic non-linear molecule for a vibration with parallel nature, it is giving PR branch means delta J is equal to plus or minus 1. PQR means delta J is equal to plus or minus 1 and 0. Q is for delta J equal to 0. We have already mentioned here for a delta J is equal to 0, this branch is written as Q branch and that spectrum will obtained here. The Q branch will be here means delta J is equal to 0. That is for delta J is equal to 0 case, if J double dash is equal to 1, J dash is equal to 1 only. Now delta is equal to mu bar 0 plus B into J dash minus J double dash. It will be 0. So no need to look for the remaining term. It will be mu bar 0 plus 0 only. That is mu bar 0. That means Q branch we will get at the correct midpoint. That is this branch is known as Q branch. Q branch is delta J equal to 0. The energy will be mu bar 0 only. That is no more rotational transition. Rotational transition is there but between the same number 1 to 1 like that. Now we have to tell what are parallel and perpendicular vibrations for a non-linear diatomic molecule. For that we are considering a non-linear diatomic molecule which is water, H2O. It is not diatomic, polyatomic. It is non-linear in shape. Linear polyatomic will be linear in shape just like CO2. It is linear. This is not linear. It is non-linear. So we have to study what is parallel vibration and what is perpendicular vibration. That means a vibration is said to be parallel vibration if its principal axis means which is come in group theory, the main axis of rotation of a molecule, the principal axis is maintained. If that principal axis is not maintained before and after the vibration, it is called perpendicular vibration. So when we tell from the starting, we can say that for a molecule, whether it will be linear or non-linear, we have studied that the total degrees of freedom, that means total type of transition it can undergo. For linear molecule it is 3n and for non-linear molecule it is also 3n, where n is the number of atoms. So if we are taking CO2 as an example for linear and water as an example for non-linear, this 3n will be equal to 3 into 3 because 3 atoms are there. So 9 total transitions are there. Total transition means transitional plus rotational plus vibrational. For this CO2 there is also 9 total transitions or total degrees of freedom we can say. In that total degrees of freedom, how much translational degrees of freedoms are there? It will be 3. Whether it is linear or non-linear, the total translational degrees of freedom is 3 because x, y and z axis are the 3 possible translational motion. And for the number of rotational transition for a linear molecule is 2 only, and for a non-linear molecule the possible rotational transition is 3. So if we are considering these factors, the vibrational transition will be equal to, first we consider the total degrees of freedom, and subtracting translational and rotational from this total we will get how much vibrational. That means here 3 plus 2, 5 is the translational and rotational together. So total is 3n. So 3n minus this 5 will give number of vibrational transition. For this also 3n minus translational 3, rotational 3, so 6. 3n minus 6 will be the number of vibration. That is simply like this. That is number of vibrational transitions, number of vibrational modes, types will be equal to total degrees of freedom minus total possibility minus the types in rotation and translation, which will give the types in the number of modes of vibrational. Number of modes of vibrational transition will be equal to total modes minus rotational modes plus translational modes. So this much vibrational and vibrational modes are present in this molecule. So now we are considering CO2. 3n minus 5 will be equal to 9n minus 5. That is 4 vibrational modes are present for CO2. Like this for water molecules, 9 minus 6, that is 3 vibrational modes are present for water molecule. In these vibrational modes there can be stretching and bending modes. In any vibrational modes there are stretching and bending types. In stretching there are symmetric stretching and asymmetric stretching. In bending the possibilities are in plane and out of plane, which can be represented with several terms like scissoring, wagging, etc. The bending is represented by different terms. For stretching, the two possibilities, symmetric stretching and asymmetric stretching. And the number of symmetric stretching will be equal to n minus 1. So total degrees of freedom is 3n for both linear and non-linear. Total vibrational mode is 3n minus 5 for a linear molecule, 3n minus 6 for a non-linear molecule. Within that vibrational modes, number of symmetric vibration which will be equal to n minus 1. So if we are considering again CO2 molecule, the total degrees of freedom is 3n, that is 9, and rotational vibrational mode is 3n minus 5, which is 4. Within this 4, symmetric stretching vibration, not symmetric, total stretching vibrations, not symmetric, total stretching vibrations will be equal to n minus 1. N is 3, that is 3 atoms, 3 minus 1, 2 stretching are possible. 2 stretchings. So which are the 2 stretching? One is symmetric stretching and other is asymmetric stretching. Now how we represent symmetric stretching for a CO2 molecule? Symmetric stretching means both from away, both to same manner. If this is away from central atom carbon, the stretching for this part is also away from central atom. This is symmetric, similar manner. This is away from central atom and this stretching is also away from the central atom. So this type of stretching is called a symmetric stretching. So in this symmetric stretching, first we are considering the principal axis for CO2 molecule. We know the principal axis according to group theory. for CO2 molecule is C infinity, because if we are considering these three atoms as balls, we can rotate these balls in 1 degree or 2 degree, 3 degree, in any of the angle. It will give the equivalent orientation, same orientation. So we will represent that type of rotation as C infinity. So C infinity is the principal axis of CO2 molecule. So this is the case of before vibration. And after vibration, which means symmetric stretching is done. If we done this symmetric stretching, so this is before stretching, before symmetric stretching. That means before vibration. The vibrational type is symmetric stretching. And after symmetric stretching, what will happen? This bond will be long and this will be lengthened like this. Now also, if here C infinity is possible. Now also after vibration also C infinity is there. If we are rotating these three balls in this axis, no changes are there. C infinity is maintained. C infinity axis is present. So C infinity is present before vibration and C infinity is present after vibration. Such transition is known as parallel vibration. So for CO2 molecule, the parallel vibration is symmetric stretching. So if the vibration is symmetric stretching, if the vibration is parallel vibration, it will give parallel, it will give PR branch. Now we check for the second type of vibration present in CO2, that is in CO2 molecule. Total vibrational modes are 4. In that total vibrational modes, stretching vibrational modes are 2 because n minus 1. So stretching is 2, so bending will be 2, then only total 4 we will get. In total vibrational modes, 2 is stretching and the other 2 will be bending. In stretching itself, there are symmetric and asymmetric. So we considered symmetric. Now we are going to consider asymmetric stretching. So now we are considering the symmetric stretching, which is the second possible vibration. There are 4 possible vibrations for CO2. First one is symmetric stretching. Second one is asymmetric stretching. Asymmetric means if this is the molecule, if one bond is lengthened away from the central atom, another bond is pushed towards the central atom. So one is away, one is towards. So two different type of actions. Now it is called asymmetric stretching. So after this, so before the vibration there is C infinity is present, and now we are checking after vibration. After vibration, what will happen? This is pulled away. So this bond is lengthened and this bond is pushed towards. So it will be smaller. Now also, if we are considering the C infinity axis, it will be present. That means no change. According to group theory, if we rotate these 3 balls, it will occupy the same position, same orientation it will give after rotation also. So C infinity is present. Now C infinity is present before and after the vibration. Such vibrations are said to be parallel vibration. So for CO2 molecule, its asymmetric stretching is an example for parallel vibration. So that vibrational transitions will give PR branches. So this is the second possible vibration in CO2. In the third possible vibration is bending. And fourth one is also bending. So which are the 2 types of bending? One will be in plane and another will be out of plane. So these are the if this is the CO2 molecule, this is the plane of the molecule. And this is a plane perpendicular to the plane of the molecule. So if molecule is present in this plane, it's a plane perpendicular to that plane. So if we are considering bending in plane means within this plane, that means this, so this is the plane of the molecule. So within this plane means bending occur like this. Oxygen is pulled like this, this oxygen is pulled like this, we will get like this. So bending occur within the plane only. Out of plane means not in this plane, in some other plane, that is out of plane. That means the CO2 molecule will bend like this. Out of the plane means in a different plane, that is this plane they are meant for. So this plane and both the planes are different. These are the plane of molecule, and this is a plane perpendicular to plane of the molecule. For example, if this is the CO2 molecule, in plane bending means like this it will bend in the same plane of the molecule. Out of the plane means away from that plane, that means like this towards upper side. So this is one type of bending like this, and this is the bending away from the plane like this, it will lifted up. This is the bending away from the plane. So in this in plane bending, if we are considering, this is the principal axis C infinity. So this is the case before vibration, and after vibration means after bending it will look like this. So if we are considering C infinity axis here, there is no more symmetry. If we rotate the molecule along the C infinity axis, what we will get just opposite of this orientation. Okay, so there is no C infinity present. So before C infinity was there, after no C infinity. Such type of vibration in which principal axis is not maintained or principal axis symmetry is lost is known as principal axis is lost is known as perpendicular vibration. So for CO2 molecule, bending in plane is a perpendicular vibration. Now we are considering bending out of the plane. Out of the plane means it is bended to downward of the plane. So we will get before vibration C infinity is present. After vibration it will look like V shape. It is bended into inner part. So we C infinity is not present. So it's also this type of bending, that means bending out of the plane is also a perpendicular vibration. So both the bending in plane and bending out of the plane, both are perpendicular vibration, and these two vibration will give perpendicular. If we can pronounce Q here, perpendicular. So PQR. Now we cannot easily forget. If we study like this, perpendicular will give PQR branch. So in conclusion, linear diatomic molecule will give PR branch, and linear polyatomic molecule will give PR branch, and linear polyatomic molecule with respect to whether the vibration is parallel and perpendicular. If the vibration is parallel, it will give PR. If it is perpendicular, it will give PQR. And for non-linear polyatomic, whether it is parallel or perpendicular, it always give PQR branch. So here linear diatomic will give PR, here non-linear polyatomic will give PQR. That means here the delta J is plus or minus 1, here delta J is plus or minus 1, here delta J is Q indicates 0 and plus or minus 1. Here the selection rule for delta J is again 0 and plus or minus 1. So in the earlier part this is wrong. I mistakenly said this is the case of non-linear and this is the case of linear. Just note that there was a mistake. This is the correct one. We checked the parallel and perpendicular vibration for a linear polyatomic molecule like CO2. Now we can also check the parallel and perpendicular vibration for a non-linear polyatomic molecule like H2O. What's the difference is for a non-linear polyatomic, whether the vibration is parallel or perpendicular, it will always give PQR branch in the rotational vibrational transition. So now we are coming to the case of H2O. So total degrees of freedom, that means total modes of motion, is total degrees of freedom is 3n, that is 3 into n, that is 3 into 3, 9. And vibrational degrees of freedom or total number of vibrations, total vibrational modes, vibrational degrees of freedom will be equal to 3n minus 6 for a non-linear. If it is linear, it will be 3n minus 5, that is 9 minus 6, that is 3. So 3 vibrational modes are there. 3 vibrational modes. There will be stretching vibrations and bending vibration. So number of stretching vibration is n minus 1, that is 3 minus 1, 2. 2 stretching vibrations are there. So which are the 2 stretching? Symmetric and asymmetric stretching. So total 3, in which in this 3 vibrational 2 are stretching vibration. So the remaining is only 1. 1 will be the bending vibration. So the 3 vibrational modes of water molecule is 1 symmetric stretching, another asymmetric stretching, and the third one is bending. In case of CO2 there was 4 modes, 2 stretching and 2 bending. Here only 1 bending. So first we consider symmetric stretching. So this is the H2O molecule. Symmetrically means if this bond is pulled away, this also pulled away. So after vibration what we will get? This bond is lengthened. So the principal axis for H2O molecule is this axis. This is C2Z. We can see this in group theory. So this is the main axis for water molecule. So before vibration C2Z is present, because if we rotate C2, that means 180 degree in Z axis, same orientation we will get. That's why we say C2Z is present. So if we get same orientation while doing C2Z here, we say C2Z is present. So this is the first before rotation. This is the case. This is the condition. And we are rotating like this. After rotation this H will come here and this H will go here. But the orientation remains same. That means C2Z is present. So here C2Z is present and here C2Z is present. So before and after vibration, both the in both the cases C2Z is present. So such vibrations are called parallel vibration. When we consider the second type of vibrational mode, that is asymmetric stretching. So this is the case before stretching. Asymmetrically we are stretching. That means if one is lengthened away, another bond length is changed towards the central atom. So after vibration it will look like this bond is lengthened and this bond is small, shortened. Okay. Now we are checking C2Z is present or not. C2Z is present here because after 180 degree rotation same, this hydrogen will go here and this hydrogen will go here, but its orientation looks same. It is equivalent, both are equivalent. So C2Z is present before vibration, and after vibration when we check, this is the C2Z axis. If we rotate 180 degree in Z axis, this short hydrogen will come here and the long hydrogen will come in this side. So both are different. Here shortened part is here, and here the short length hydrogen is in the left side. So that means both are not equivalent. That means C2Z axis is not present, or C2Z symmetry is lost. So for a water molecule, this asymmetric stretching is an example for perpendicular vibration. Now we are considering the third vibrational mode, which is bending. So bending, there are two possibilities, in plane and out of plane, but for for water molecule only one bending is there, that is in plane only. That means if water is present in this plane, the bending occur within this plane. So in this plane bending occurs. So after bending we will get in the same plane bending occur. So like this we will get, means it is bended like this. Okay, so now we are considering the principal axis. C2Z is present, means if we are rotating it is 180 degree, this hydrogen go to this side and this hydrogen will go to this side, same appearance. So C2Z is present. For this condition, if we are considering C2Z, then also this hydrogen will go to this side, this hydrogen will come to this side. So after rotation also same appearance we will get, that is C2Z is present. So C2Z is present before and after the vibration. Such vibrations are called parallel. So whatever be the vibration, parallel or perpendicular, as it is non-linear, it will give only PQR branches. The conclusion of this section is this only thing we have to study in this part. We just said example for parallel and perpendicular vibration, that's all.